Okay, so I want to look at example 4.1 in this video, and there we're given an expression for ln p. So basically this expression just says ln of p is equal to 18.361 minus 3036.8 over t. It just gives the units of the pressure and the temperature is in Kelvin, so that you know what these constants are given in. So that's what the expression is, and then it says what is the enthalpy of vaporization of the liquid. Now you can do a few things. You can rewrite it in terms of P, so that you can get an expression for P, and then you can plug it into the Clausius-Clapeyron equation, and then you can calculate delta the enthalpy of vaporization. But remember, you need to calculate or plug it into the differential form of the Clausius-Clapeyron equation. Why? Because we're given a function. We're not given a pure value of P here. So the trick to this kind of question is, because we're given a function, we need to look at the steps where we actually derive the Clausius-Clapeyron equation. Now, the one that I identified is actually here, where we write something where we say dP over P is equal to the enthalpy of vaporization over R, not that, dt over t squared. So there's a step where we say something like that. Then in mathematics there's a little nuance where it says, so this then what caught my attention was this dP over P. Now dP over P is actually the same as d ln of P. So you can immediately see why I'm interested in that, because then we can just use the equation as it's given, or actually the differential of the equation as it's given, because then we can just do some rewriting of the equation. But anyway, so just to explain why this is what it is. So if you have, if you look at this function here, right? So, oops, still haven't figured this out. What you have here on the left hand side, technically you have here dP, and then P is some function of some variable, and believe you have it as some function of some variable. When you have d ln of a function, which is a function in itself, then its derivative will be, right, so ln's derivative is always 1 over the function, right? But this is a function, so it's in itself will also need to have its derivative. So in other words, we need to take the derivative of that function as well. And then you see that top part pops out. So actually the derivative of ln of a function, so maybe if I write it without the p's and I make this like, you know, like what you did in high school, you know, you wrote an f for function, then it becomes a bit more apparent. So if you have the differential of ln of a function, then you write it becomes 1 over the function times the differential of that function. So that's why we can make the substitution into our equation here, that this is actually d ln of P, because P is a function in this case. It's not just a value, it's a function. So it's very handy to have a notion of what is functions. You know, R is just a value, it's just a constant. But T and P in these cases are actually functions. So you can make these swaps with them. Then especially if P is going to be a logarithmic function, then you can make this swap. And now if I take across this dt, so take the dt to this side, in other words, you know, divide by dt on both sides, then I divide by dt, then I get a nice expression, t squared, that I can use. Because what do I have now? I can write for delta, for the vaporization enthalpy, I can write that RT squared times d dt of the ln of P, right? And what is the ln of P? It's this function that we're given. I think it's very clever. Okay. I know, I'm very clever. Anyway, so let's just plug this function in. So I think there should be some option for me actually just to copy it. But, no, I've lost it. I've lost it. That's okay. Such is life. Life happens, you know. I can still do this. I'm gonna have to, otherwise my thing looks ugly. So plugging this in, we have RT, of course, RT squared, and then we have d dt of this function. So what is d dt of a constant? It's 0. So the first part becomes 0. So we have RT squared times 0. And then we have minus 3036.8. And what is the differential of 1 over t? It becomes minus t squared. So in other words, we have a minus 1 over t squared here. Okay. So we write this out. So that first part is just 0. We see that t squareds will cancel. The minuses will cancel. So then we're just left with 3036.8 R, which is quite easy to calculate. So I mean 3036.8. That's of course in Kelvin. I think that's the value that they give up here, if I'm not mistaken. Yeah, 3036 Kelvin. Let me just select this. Of course, when I want to select the thing, it doesn't select, and when I don't want to select the thing, I struggle to select it. Of course, now my writing is going to be at the wrong place. So that's in Kelvin. So we're just able to cancel our units. So that's Kelvin. And then R is 8.3145 joule per Kelvin per mole. Okay, so the Kelvins cancel, and then we're just left with joule per mole, which makes sense because we're dealing with enthalpy. So if you plug that into your calculator, you will get an answer of 25249.4736 joule per mole, which of course rounds off to we move 1, 2, 3 to 25, and our significant figures is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, so 5, 1, 2, 3, 4, 5, so 249 kilojoule per mole. Yeah, it's a very nice little example. There's another similar question in the question sets of the exercises for Atkins, which will use the same trick again. So that's why I did this, because I thought it might be a bit challenging. Well, specifically why I did this kind of example. So yeah, just to wrap your head around this kind of idea is basically just to remember that a function, of course, has an inside function. So you have ln of a function, which is not just a value. So it's not just ln differential, it's just 1 over that thing. That thing has a differential in itself, which is, of course, that thing. And then you can, then from there on, it's actually quite easy. Yeah, I hope this was helpful.